Okay, so for this question then, we've been told that a sample of bromine was analysed in a time-of-flight mass spectrometer and contains two isotopes. After electron impact, all the ions were accelerated to the same kinetic energy, and then they travelled through a flight tube that was 0.95 metres long. The 79 Br ions took 6.69 times 10 to the minus 4 seconds, and we have to calculate the mass in kilograms of one ion of 79 Br and then the time of flight for the 81 Br ions to travel through the same tube. Now all I've done is just highlight that key information and identified the values that I have. So I have a distance and I have a time. I'm going to start by then working out the mass of the 79 Br ions. So I'm just going to make note that these calculations apply to 79 Br. And we're going to start with the mass. So in order to work out the mass then, I'm going to have to use the molecular mass, and I'm going to divide that by 1,000 and multiply by Avogadro's number. 10 to the 23, not minus 23. That will give me a mass in kilograms of 1.3119 times 10 to the minus 25 kilograms. Now, I can put that in my space to write my answer at the bottom. I'm just going to leave it for now, and I'm going to carry on with my calculation because we've also been given in the question the distance and the time of the 79 Br ions. So what we can do is we can use them to work out the velocity of the Br79 ions to then use that in the kinetic energy calculation. So the velocity is going to equal the distance, which we said was 0.95, divided by the time, which was 6.69 times 10 to the minus 4, which tells me that the velocity of those ions is 1,420 meters per second. So now I've got that, then I can use my kinetic energy equation. So I've got the kinetic energy equals half multiplied by the mass times the velocity squared. So I'm going to have a half times 1.3119 times 10 to the minus 25 times 1,420 squared, which tells me the kinetic energy of the bromine 79 is 1.3227 times 10 to the minus 19 joules. Okay, now the question told us that they both had the same kinetic energy. So this is the kinetic energy for the bromine 79 and the bromine 81. So we can assume then that we can use that calculation, we can use that value to work out the time of the bromide ions with a mass of 81. Now, in order to get the time, we're going to need the velocity again. So in order to work out the velocity, I'm also going to need to work out the mass. So again, my calculation is not finished. As I said, this is a big calculation to do, so take your time, work through it. So we now want the mass. This time we're working with bromine 81. The mass is going to be 81 divided by 1,000 times 6.022 times 10 to the 23. And the mass this time is going to be 1.345 times 10 to the minus 25. Now we've got the mass, we can use our kinetic energy equation. So I'm going to rearrange that to work out the velocity. So rearranged, it's going to be the square root of the kinetic energy divided by 0.5 times the mass, which will give me the kinetic energy from before, which was 1.3227 times 10 to the minus 19 over 0.5 times our new mass, 1.345 times 10 to the 25, which tells me the velocity here is 1,402 meters per second. I've then got to work out the time, so I'm going to rearrange the velocity equals distance over time. Time equals distance over velocity. We were told the distance was 0.95 originally in the question, divided by 1,402 will give me an answer of 6.77 times 10 to the minus 4. That is a big question. Okay, very easy to get tangled up. So look through the mark scheme. What do we pick up the marks for? Where have you dropped answers? If you have, if you haven't, fantastic, well done. Finally then, just 8.1. Let's move that down quite a bit. So we have to explain how ions are detected and relative abundances are measured. Remembering that relative abundances is essentially the relative amount of that particular species. So the first thing that's going to happen here then is that the ions are going to hit the detector. Now when they hit the detector, they gain an electron. And gain an electron. And the actual relative abundance measured, the relative abundance is proportional to the size of the current. So it is the size of that current that is produced by the gaining of an electron that produces the actual signal. So relative abundance is proportional to the size of the